Hello students, today we are in lecture number 12 of chapter 1 Electrostatics. Student, in last lecture we have discussed about the electric dipole. Today we will study how to find electric field due to electric dipole at different point. One point we have discussed axial point, and another point we have discussed equatorial point. Today, first we will derive mathematical expression for the electric field. Electric field due to dipole 1 at axial point. This is also called end on position. Okay, this is end on position. Student, we have discussed that end on position or the axial point, it lies at the axis of dipole, that is the on line joining two charges. Suppose it is a dipole plus q and minus q. Dipole is a system of two charges having equal and opposite magnitude. For simplification, we have studied distance will take as a 2a. From center, we have to find electric field at certain distance, say x. At this point P, we are going to find the net electric field, and this distance is x. Okay, we have to find electric field at point P. Due to positive charge, the electric field will be away. This is due to positive, and due to negative, this will be towards the charge E minus. We will consider this direction as a x axis. Okay, student. Now we have to find electric field at point P due to this positive charge, and this positive charge is, this distance is 2a, and this distance we don't have, so we'll simply take with respect to this x. This is x and this is 2a by 2, that is a. So the total distance for this positive charge from observation point, it will be this distance, it will be x plus this is a, x plus a. And for negative charge, for this negative charge from observation point, that this distance will be, this is x, and minus this a will give you the separation between negative charge and observation point, that is x minus a. Remember, this 2a is dipole length. Okay, this is dipole length. Now student, we have to find the electric field at this point P, and net electric field we can write it is in vector form as E plus going towards positive x-axis. So here the E plus I cap plus E minus I cap. This E minus towards the negative of x-axis, so minus I cap. Overall, we can write here the E plus minus E minus I cap. Here we have been taken the negative sign of this minus I cap. Remember, this subscript negative only a representation, as if I write here the QA and QB, then A and B. Same way, I am using here the plus or minus only the symbolic notation. You don't have to use this minus or plus in calculation. Now student, E plus. the formula of electric field, we know that it is kq by r square, that is the square of separation. So the positive charge is separated by x plus a, so the kq over x plus a whole square, minus for the negative charge kq by the distance, how much, x minus a, kq by x minus a whole square. Here I cap will simplify, take LCM, x plus a whole square, x minus a whole square. Here kq, it is kq, here x minus a whole square minus x plus a whole square. This is a simple calculation you can do by yourself in better way. I'm just rubbing this one, electric field due to dipole. Now this one, kq, okay, x minus a, this will give you x square plus a square, x square plus a square minus twice ax minus this minus sign, x square plus a square minus x square plus a square plus twice ax, and with this negative all the terms will be negative, so the x square minus a square minus twice ax, and I cap here this one over x plus a into x minus a whole square, and this is x square minus a square, x square minus a square whole square we can write. I hope you are getting. The next one, cancel out this x square and a square, kq, this is minus twice ax over here the x square minus a square whole square, here x plus a times x minus a, x square minus a square and whole square, and this is nothing but the net electric field with the direction I cap. So this is the electric field. Now student, if we'll simplify this equation for the short dipole, because this is very important derivation and you will be asked in your board examination in alternate year, either the electric field at axial point or at equatorial point, this type of derivation will be asked, or numerical on the basis of this derivation. Student, we can write this equation in terms of dipole moment as this one. In terms of dipole moment, E is equals to, it is the q times 2a will be q times 2a. Try to recall, q times 2a, it is the dipole moment. Okay student, so the q times 2a will give you the dipole moment p. So it is k p x over x square minus a square whole square, and this minus I am taking with the direction, it is minus I cap. So the kpx over x square minus a square whole square. This is another standard equation you will use for the electric field due to dipole at axial point. Now if you will be asked as the simplified case for short dipole, that is if this dipole is very small, as we know that the dipole is charge in dipole are separated with the very small vector distance, so this a will be much less than, very much less than x, which is the observation length. So this will be a much less than x, and this a can be neglect, so this e can be written as neglecting this a, k p x over x square whole square, here a neglected, tends to be 0, minus I cap, and it is equal, this x will be cancelled out, kpx over x4 minus I cap. This x will be cancelled out and we'll have a simple equation that would be easy to remember also. E net at axial point, it is kp over xq, kp over xq with the direction minus I. Now student, you can see this equation giving you another concept also. Here, what is the direction between electric field when we talk about the electric field at axial point? What is the direction between angle between electric field and dipole moment? Look at here. Here the electric field we are getting in minus I. Okay, electric field we are getting in this direction. This is the E net. In case of axial point we are discussing. Okay, so this is the electric field. Now the dipole moment. Here the dipole moment, it is the minus q and plus q, as we know that the direction of dipole moment must be towards positive charge from negative charge. So the direction of dipole moment will be the same. This is the direction of dipole moment. So we can write a very important note about this one. The electric field at axial point must be in the direction of net dipole moment. That is, the net electric field must be in the direction of dipole moment in case of axial point. So student, this is the simple formula you have to be bear in your mind, that is kp by xq minus I, and this minus I representing the direction of electric field. Now the second derivation at equatorial point. Equatorial point. Okay student, you know that what is the equatorial point, we have been discussed so already. What is the meaning of equatorial point? Line perpendicular to the axial line will be considered as the equatorial. Okay, so this is the equatorial point. This is the diagram we are drawing. Here the plus q charge and minus q charge, both are separated by 2a. Again it is 2a, that is from center it is a, and this is the axial line. This is the axial line. At this point we are going to find out the net dipole moment. From this positive charge and this negative charge, we can draw here the distances. If this is x distance above the center point and this is the p, we are going to find out the net dipole moment. Due to this positive charge, the electric field will be away, this is E plus, and due to negative charge the direction will be in this way, E minus. And here this is the x-axis and this is the y-axis. Okay student, suppose this is the angle theta. Of course this will be also the theta. If this is theta, then this will be theta, and for this angle, this is angle theta, we can write as the theta. Okay, now E plus and E minus having the same magnitude. Here the E plus and E minus having the same magnitude. Okay student, here the E minus, both are having the same magnitude. Suppose it is E. Okay, so this E will have the two component. We can write it the E here, E cos theta, E cos theta, and E sin theta, E sin theta, and this one having E cos theta, E cos theta, and this E over here, E sin theta. So another E sin theta. Since both the component are same, the angle are same, this will be cancelled out. So we'll have the net electric field E net will be how much? It is twice E sin theta. Okay, now we'll find the value of this one. So it is the twice E sin theta. Now we are finding here the distance, this one, from the positive, this point P is at the same distance as this negative charge from the point P. Let this distance as the Z. Okay, now this Z will be how much? Actually, this is the root under, this Z is root under a square plus x square. A square plus x square. And we can write here that 2 E is kq over the distance square, that is the Z square, and sine theta. And sine theta we can write here using this triangle. Sine theta can be written at the P by H. So the perpendicular will be A and H, that is the hypotenuse, it is Z. Okay, so we can write here the 2kqa over this is zq. Now the direction actually, student, so we are getting here along x axis. You can see the 2 are cancelled out, only we are having the value along the x axis, and this can be also written as q times 2a. Try to arrange q times 2a. This 2a times q will give you the dipole moment, that is p. So the kp over z, and z what is a square plus x square root under, that is half. So the a square plus x square half to the power 3. Okay, and this will be equals kp over a square plus x square to the power 3 by 2 along x-axis. This is the net electric field. So this will be the electric field formula in case of equatorial point. Now again we are just going to apply for the short dipole. For short dipole, that is a much less than x, a much less than x, and this x can be, a can be neglect, so this will be the xq. E net will be kp over xq. Look at here, thus a will be neglect, x square and this power 2 will cancel out, so the xq will have, and the direction remain I cap, so the kp by xq, and this is the net electric field. Now again we are going to analyze here the what will be the direction of electric field and dipole moment. What is the relation between this direction of electric field and dipole moment? What is the angle? If the question is asking what is the angle between net electric field and dipole moment in case of equatorial point, so you can see easily over here, student. This is the direction of electric field, in which direction? I cap. So this is the E net in case of equatorial. Okay, this is the net electric field. Now dipole moment from negative to positive, so the dipole moment here it is P, and the angle will be how much, student? Angle will be 180 degree in case of equatorial, and in case of the axial the angle was how much? It is 0 degree. So this is the electric field due to dipole. Now student, I am leaving you a question. Okay, how will you, can you note down, how will you find the electric field at an arbitrary point due to this dipole? Here you are having the dipole, this will be your homework. Okay, this is plus q and minus q, again the distance 2a, and this is the center of the dipole. Here from dipole at point P, for simplicity I am writing here minus q and plus q. Okay, this distance is given actually from observation point, the center is r distance away. Negative to positive, the dipole moment in this direction. Here the angle is also given, suppose it is theta. You have to find the net dipole moment at P. What will the question? Derive mathematical expression for net electric field due to dipole at arbitrary point. Remember students, I am writing the same question that will be asked in your board. Actually, this is the question and this will be the diagram. How you will find the net electric field due to this dipole at arbitrary point. So this will be your homework. Try to solve by yourself. Now student, the next derivation we are moving for, this is the torque due to dipole. Could you recall me students, what is torque? Then we'll in position to study the torque about this dipole. Suppose this is the electric field. Here, net electric field. We're taking the direction X, Y and Z. Here we are having the electric field, the topic I'm writing here, torque on dipole placed in uniform electric field. Okay, here E, it is E j cap along the y-axis. We are placing here the dipole negative Q, that is minus Q and minus Q and minus plus Q. Okay student, this is direction of electric field, direction of electric field. Now this dipole is maintained in this field by external agent. As soon as this dipole will leave, it will start rotating. This negative charge will move opposite to the field. As we know that negative charge move always opposite to the field, electric field, and this positive charge will move up, and resulting here the two forces are acting here, this one force and the second force. It will start rotate. If any body rotating, there must be some net torque acting. So we are going to find out this dipole will start rotating from this point. This distance is 2a. Okay, this will be a and this will be also a. We are going to find out here the net torque. Again here we can draw the diagram. The diagram only will make your concept clear. After rotation, okay student, thus negative charge, here only I am writing the minus, you know, here the minus Q and plus Q. Why this is moving? Here the QE acting the force, and here also QE acting the force from the center. Suppose from minus to plus, a dipole moment P making an angle theta with the electric field. This is the direction of electric field. So this is making an angle theta with the electric field. What was that length? This length was A and this length was also A. Okay. Now student, here the net torque tau net will be 2 torque, tau 1 and tau 2, that is due to the positive charge and due to the negative charge. Here I am writing the net torque. So this torque can be written as the, you know, the torque, it is QE, I mean the force into perpendicular distance. Here the force is which one? QE. Force and perpendicular distance. The perpendicular distance here, if you just project this force, you will have perpendicular distance is this one, and this is not the A actually. Remember, now A is this one. So you will have to, if this is theta, this will be theta, then you have to break the component. This A will have the component as A sine theta, A sine theta, A sine theta. Over here also this will be the A sine theta. Okay, so the A sine theta will be the perpendicular length. So A sine theta, and the direction dipole is rotating in this way, try to recall to find the direction of torque. As I taught you in chapter rotation, to find the direction of torque you must have to remember the rotation of a cap, dhakkan. Okay, so this will rotate in this way. Okay, if it is rotating, if cap is rotating in this way, because this dipole will rotate in this way. If cap is rotating in this way, then the cap will remove and it will move up. So this direction up is considered the positive k, plus now this tau 2, this force will also rotate in the same way, so the direction will be same. Okay, and the magnitude, again force, it is QE, and the length again is sine theta, and the direction is k cap. Remember students, in few books it is written directly you can take the length of this one. Okay, and you can make the component, if this is the theta, then this will be the also theta, and this 2a will be written as the 2a sine theta. Yes, you can solve by that way also, that is not the incorrect. Okay, how you are getting. If you are not able to understand, then you can take the help of other book. Thus, or if you will be study in that book, never be confused. This 2a will be, if this is theta, then this will be also theta. If you will break this 2a as component, this will be the 2a sine theta, and you can write directly because both the directions are same. Now, so the net torque, it is the net torque can be written as, it is in vector form. It is, since both are same, so the 2 QE a sine theta and direction k cap. Here the 2a and q times 2a will be give the p, okay, and e, here the sine theta and direction k, tau net. Now look at carefully students, since it is the p e sine theta and having the direction, that is the magnitude and direction, this is the vector quantity, so you can write, and since this p is also vector quantity, e is also vector quantity, so you can write this one in vector form also as the cross product. Tau net, it is p cross e. Now if you will ask, why sir p cross e, why not e cross p, then I'll tell you, if p cross e, then this is the direction of p and e in upward, so the p cross e will give you the direction upward. If you will make e cross p, then e is above and p is in this direction, so p cross e will give you the direction of torque downward, which will be the wrong. We are having the direction of torque in upward direction, so we are writing as the p cross e, not the e cross p. And this is the very important formula. This is also the very important formula. The magnitude will be here, magnitude of torque is magnitude of torque is pe sine theta. Okay, try to remember this pe sine theta. This is the magnitude. Now student, if you will be asked to find the work done by rotation of this dipole, what will be the work done, how much work is done by the dipole in rotating, okay, or how much work will be done by the external agent, so you can also find that work done. That is not the very tough, student. Here, work done by dipole, work done by dipole in uniform electric field. Okay, suppose dipole is rotated, here q, I'm writing e, and this is the direction theta with the dipole moment. Okay, so the angle between p and e, it is here theta. Work for very small angle we are rotating this dipole. Okay, so the very small work done can be written at the tau d theta. In rotation you have been studied tau d theta. So the tau d theta dw, you can write here the tau we have been studied right now, pe sine theta times d theta. Okay, to get the total work, we have to rotate this dipole. If it was in a stable state, then the angle will be, this theta will be 0. If it is in unstable state, then this theta will be 90 degree. So from stable state, if you are rotating to find the maximum work, so from 0 to 90, you have to leave to rotate it. From 0, the dipole is in this way, and you have to rotate in this way by external agent. By external agent here. If you are giving the limit from 90 degree to 0 degree, then this will be by dipole itself. You're not required to just rotate this dipole. You will leave and it will automatically move to the 0. This will be the dipole itself. Here the work done, P E, and integration of sine theta will be minus cos theta from 0 to 90 degree, P E minus cos 90 to cos 0. How much this is? 0. Okay, how much this is? Cos 90, 0, and this will be 1. So P times E, this will be the work done by the external agent. If you will be asked to find the work done from 0 to theta, okay, from 0 to theta, then you will, that is the work done by dipole from 0 to theta, or the external agent to work for very small angle. So you can integrate this one dw as P E sine theta d theta from 0 to theta, or if you will be asked from here theta to 0 or theta to 90, how much work will be done, then you can find out from here 0 to theta. You can find another, okay, derivation. So this is all about today lecture, students. In the next class we'll study about the solid angle and Gauss law and theorem. Okay students, thank you very much.